Hey Ramblers! This video covers chapter 5.2 in our textbook and deals with the definite integral. This video is going to pick up where the last one left off. That is, we're trying to calculate the area underneath a curve. Now, in the last video we did that by breaking that area up into subintervals. And we made a rectangle, or built a rectangle, off of each subinterval. Sometimes our rectangles overestimated, sometimes they underestimated the area under the curve. But when we added them all up, we got a pretty reasonable estimate. Now hopefully you also noticed that the more rectangles we took, the closer our overestimate and our underestimate became. So it makes sense that if we take more and more and more of these rectangles, we're going to get a closer and closer and closer fix on what the exact area is under the curve. Well, writing out all those areas of rectangles would get really, really long. So we need to introduce you to a new kind of notation called sigma notation. And the obvious conclusion would be, well, if the more rectangles you take, the more accurate you become. What happens if you take the limit as the number of rectangles goes to infinity? So we'll introduce you today to the definite integral, which is the result of that limit. Now, a couple of side notes before we wrap the video up. We're going to talk about what happens when the area is below the x-axis or below the horizontal axis, and then we want to introduce you to a couple of vocabulary terms, specifically Riemann sum, because that's a term that is introduced in calculus, used frequently, but there's a little bit of misunderstanding about that I don't want you going off to your next math class without making sure you understand. So please pause often, take good notes, and thanks for watching. In the last video, we were interested in estimating the area under a curve so that we could calculate the distance traveled. So we broke that area up into rectangles. There were two types of rectangles. We had left-hand sums, whose height was from the left side of each subinterval, and right-hand sums. And sometimes the left-hand sum overestimated and right-hand underestimated, or vice versa. Sometimes the left-hand sum underestimated and right-hand sum overestimated. It all depended on whether the function was increasing or decreasing. As the number of rectangles increased, we saw that our estimate became more and more accurate. And you can see by the picture here, as we increase the number of velocity measurements, we see an increase in the accuracy of the rectangles as they approximate the actual area under the curve. It gets to be a better and better and better fit. And then lastly, this kind of came up in the in the exercises, that area above the horizontal axis had a positive sign associated with it, and area below the horizontal axis had a negative sign associated with it. It's not that area is negative, it never is, but it can have a sign in front of it. So to make all our calculus work, area above the axis is positively signed, area below the axis is negatively signed. All right, that's what I want to make sure you know as we move on to this next section, 5.2. After we calculated the area of these rectangles, we added them up. And if we tried to add up the areas, or if we tried to write out the areas in the picture on the left, it would be tedious but not so bad. But as you can see, as the number of rectangles increases in order to be more accurate, writing out the sum in the right-hand graph would really be tedious. So we need a new kind of notation called sigma notation. So let's take a closer look at a sum written in sigma notation. Let's start with this right-hand sum above. As you can see, each rectangle has a base that is delta t. Now, an important calculation is that delta t equals the upper limit, which we call b, minus the lower limit, we call a, divided by the number of rectangles, which is n. Make sure you have that calculation in your notes. It comes up frequently. So the right-hand sum is equal to the area of the first rectangle, which is the base, times the height. the height is f of t sub 1 times delta t. Then you'd add on f of t sub 2 times delta t. And then you'd add on f of t sub 3 times delta t. And then you would keep on doing this until you got to the last rectangle, whose height is f of t sub n times delta t. And that's a really, really long series of areas to write out. So they've made that simpler by introducing to what's called sigma notation. So we write the Greek letter sigma, which means sum. On the bottom of sigma, tells us where to start. So in this case, our first I, or I should say our first height, was at t sub 1. So I equaled 1. Our last one was n. And we are going to add up things of the form f of t sub I times delta t. And we'll start where I equals 1, and we will continue until it equals n. And that becomes our right-hand sum. Now, let's see how that's different than a left-hand sum. Now, a left-hand sum is going to be very similar, except that our base is going to start in a different position. So the left-hand sum equaled the height at the height of the curve when t was equal to t sub naught times delta t, plus f of t sub 1 times delta t, plus f of t sub 3 times delta t, and so on until you get to f of t sub n minus 1 times delta t. So our rectangles are shifted over to the left, with our last rectangle getting the height from the second to last t. So if we were to write that in sigma notation, in order to save us all that writing, the left-hand sum would equal the sum of all of the rectangles in the form f of t sub I times delta t. That's the same as the right-hand sum. But now we're going to start when I equals 0, and we'll add up to n minus 1. So just to remind you, the right-hand sum equaled the sum of areas in the form f of t sub I times delta t. But we were starting, you recall, with I equal to 1 and stopping at n. This is a very important concept. You'll want it in the notes, but take a minute, pause the video, and compare this notation to the diagram here that I've just inserted at the left. Make sure you understand what a left-hand sum looks like, what a right-hand sum looks like, and how they are reflected in the differences in the notation. In order to gain more accuracy, we want to increase the number of rectangles, and it becomes a better and better fit under the curve. So we could take either the left-hand sum or the right. It doesn't really matter. I'm going to take the right because it's just more familiar to me to write it out that way. So I equals 1 up to n of f of t sub I times delta t. And that sum represented an estimate of the area under the curve. Now if I take the limit as the number of those rectangles, n, goes to infinity, I get a new new quantity that is no longer an estimate. It becomes the exact value. And so we use a different kind of rounded s, which still means sum. But now we represent the lower limit not as I equaling 1 or I equaling 0. We just call the lower limit a. The upper limit, instead of n or n minus 1, is represented as b. So we could say that a equaled 0 here and b equaled 10 for both of these examples. I'm not trying to circle the 2 there, I'm just trying to write 0. So b equals 10. And we write f of t. But now, since we're taking an infinite number of them, we don't mark which t it is. And then our delta t becomes dt. So you can see that the two notations are similar, but when we take the limit, we get a kind of a rounded s rather than the Greek sigma. The upper limit becomes represented as the actual number. The lower limit becomes the actual number where you started. F of t just stays as f of t, and most importantly, or just as importantly, the delta t becomes dt. This is the definite integral. You'll definitely want that in your notes and be comfortable what all these different numbers in the notation mean. Okay, let's take an example here. If I were to write the sigma notation for this first graph here on the left, I would say sigma. And if I were writing the left-hand sum, well, let's stay with right-hand sum since that's what I did earlier. The right-hand sum would be I equals 1 up to a total of 2 rectangles. I would say this was 1 over t sub I times delta t. Now, as I took more and more of those limits, or I should say more and more of those rectangles, I would come to the second one here, which would mean the right-hand sum would equal, still starting at I equals 1, but now I'm going up to the 10th rectangle, but my formula hasn't changed. I'm still 1 over t sub I times delta t. Well, finally, as I take the limit, I get to this last picture on the right, where I no longer have a left-hand or right-hand rectangles. I just have the integral. And the integral is going to start at t equals 1. It's going to finish at t equals 2. The curve is 1 over t times delta t. I'm sorry, but in the integral we call it dt. So that's how we write out an integral instead of sigma notation. We've taken a lot of examples in the last section when we were dealing with velocity, and most of them were positive. But what happens when f of x is negative, when the curve drops below the horizontal axis? Well, once again, all area is positive, but in this case, this area would have a negative sign. So let's get that in your notes. So if f of x is less than 0 on some interval from a to b, now you don't understand this yet, but this is where a is less than b. So a is to the left of b. Then the integral from a to b of f of x dx is a negatively signed number. The area is still positive, but it's negatively signed. By the way, pay attention to how I just said that. I said the integral from a to b of f of x dx. All right? Okay, let's take one more look at that example and then we'll talk about some vocabulary. All right, so this is a diagram we used earlier in the video. But suppose we took the integral from 0 to the square root of 2 pi of sine of x squared dx. And we would see that from 0 to square root of pi, the curve is over the x-axis. So this region has a positively signed area. Then from root pi until root 2 pi, the area would be negatively signed. Now, if we called the area above the axis, from 0 to pi, a sub 1, and the area below the axis, from root pi to root 2 pi, a sub 2, the correct value of this integral would be a1 minus a2, because a sub 2 is negatively signed. Okay, so let's just make sure we have some vocabulary straight, and then we'll wrap up the video. So this elongated s is the integral symbol, and the a and b are your limits of integration. F of x is known as the integrand. And very importantly, the delta x becomes dx in this new notation we have. Lastly, let's talk about a term that you'll see in this book and is often misunderstood, and that is a Riemann sum. And Riemann is a German mathematician who did a lot of work proving that an infinite number of rectangles would in fact equal the integral. But in his sums, an actual Riemann sum, the delta x can vary in length, and you don't have to pick either a left-hand sum or a right-hand sum. That the f of x can be any f of x within each subinterval. So when we will refer to left-hand sums and right-hand sums as Riemann sums, but they really aren't, that's not exactly correct. So we use it interchangeably, but I want you to know that in a strict Riemann sum, the delta x can vary slightly, and the height can vary within the subinterval. All right, Ramblers, a lot of information in this video. Please go back, take a look at sections that might still be unclear. Come on in tomorrow with some good questions. But most of all, thanks for watching.